Welcome to this presentation on realization. My name is Kannan Maudgalya. In this video, we will discuss what is realization. We will obtain it through state space. We will also obtain it directly. What is realization? Controller design calculations are done in transfer function domain. It is because of the convenience. So the controller will also result in the same domain, namely in Z transform. Unfortunately, it cannot be implemented directly. We need to invert it to time domain to implement it. This is known as realization. So we will start with an example. G of Z is the transfer function. It is given as the ratio of two polynomials in powers of Z inverse. Suppose we define this as B over A. Suppose the input is U of Z and the output is Y of Z, then Y is equal to G into U. When we cross multiply, that is, we substitute for G as B by A from here, then we have B into U, this A will go here, A into Y, so AY equals BU. So AY is written here, this is A, we multiply the whole thing by Y, so we have Y into Y is here, A1 Z power minus 1 into Y and so on. Similarly, B into U is this whole thing into U that we have here. So what do we do next? It is obvious. We take all the past terms to the right hand side and the U terms we keep them as they are. Now let us use the shifting theorem. So this will become Y of n minus 1 because Z power minus 1, we have Z to the power minus 2 here. So this will become Y of n minus 2 and so on. So this corresponds to the Y terms. What about the U terms? Once again we will have the same thing, B0 into U of n, B1 into U of n minus 1, B2 into U of n minus 2 and so on. So we have this expression. So let us take it to the next slide. What we will do is we will realize only the Y terms. Remember, we have both Y terms and U terms, but we will first realize only the Y terms. So let us start with this. How do we realize this? For this I am going to use a block diagram given here. Although it looks little complicated, let us focus on Y of n here. So inverse of this Y of Z is Y of n. This is multiplied by minus A3. So this is minus A3 into Y of n. When it goes through a delay term, remember Z power minus 1 is a delay. So when it goes through this, I get minus A3 into Y of n minus 1. I have minus A3 into Y of n here, and so here I have minus A3 into Y of n minus 1. Next we will see what happens when this is propagated through one more delay. So I have this, so here it is minus A3 into Y of n minus 1. When it passes through one delay, I have minus A3 into Y of n minus 2. So that comes from here, but we have an additional term that comes from here, that is because of minus A2. So that becomes minus A2 into Y of n minus 1 because of one delay. We do the same thing here, we shift the whole thing over here. So we have one delay term, so this n minus 2 becomes n minus 3, n minus 1 becomes n minus 2, and then we have a term, additional term due to this minus A1. We have minus A1 into Y of n minus 1. So let us go to the next slide. Now in a similar way we will realize the U terms also with another block diagram. Okay, recall the expression that we had for u. This can be realized as follows. Before that, what we will do is we make an observation that all sample systems have at least one delay. So we will explain this shortly. What we will do is we will take B naught to be 0. In other words, this un will not appear directly in yn, there will be at least one delay. This will be explained later. So I claim that this block diagram implements this expression with B naught equals 0. It is very easy to verify. You see that B3 into un here, it goes through 3 terms of delay. So we have B3 into u of n minus 3. Similarly, B2 into u of n minus 2, there are 2 delays, and B1 into 1 delay term u of n minus 1. So this block diagram also can be understood very easily. So we had a block diagram to realize only y terms, another block diagram to realize only u terms. Let us superimpose these 2 terms to get this block diagram. So this is straightforward. We obtained the bottom one to implement y, we obtained the top one to implement u terms. When we superimpose, we get this expression. We will continue with this, but for convenience I am introducing new symbols x1 here, x2 here, and x3 here. So we start with this. Now notice this y of n is nothing but x1 of n. So I write y of n equals x1 of n. Now I will write an expression for x1 of n plus 1. What is x1 of n plus 1? Remember, this is x1 of n. So here I need to have x1 of n plus 1. When I have x1 of n plus 1, send it through a delay, I get x1 of n. So this is x1 of n plus 1. x1 of n plus 1 is nothing but x2 of n, it comes from here. So I write it here. Then I have b1 of u of n, I write it here, and then minus a1 times x1 of n. So this is x1 of n plus 1, it is equal to x2 of n, b1 into u of n, and minus a1 into x1 of n. Similarly, you can get an expression for x2 of n plus 1 from this junction, and then x3 of n plus 1 from this junction. It has only 2 terms, b3 into u of n minus a3 into x1 of n. So it is easy to write down these equations directly by observation from this block diagram. Now we will write this in matrix form as follows. So there are 3 states x1, x2, x3. We will put them as components in this state vector. I have the same state vector at time instant n, and I have this input u of n. Look at the first equation, x1 of n plus 1 equals minus a1 into x1 of n plus x2 of n, and then finally there is no x3 term, so I put a 0 here, plus b1 into u of n. So this is the implementation of the first equation in matrix form. Similarly, write the expression for x2 of n plus 1 from the second equation. You can verify that this is correct. Similarly, do this for the third equation. It has only 2 terms, minus a3 into x1 of n plus b3 into u of n. Let us write the expression for y of n. It has only x1, the other state components are 0. So I have 1 0 0 here into the same state vector. So this is of the form x of n equals a into x of n plus b into u of n, y of n equals c into x of n plus d into u of n, but d is 0, so this term is not there. So here is the transfer function realized as a state space expression. Let us have some comments on this. The textbook explains one other way of realization through a problem. There are at least 4 ways of realizing state space equations from a transfer function. See the famous book Linear Systems by Thomas Caillat. It turns out that for discrete time systems it is also possible to realize directly without the state space approach. This will be explained with an example in the next slide. So let us have this transfer function g of z, it is given here. We write g as y by u. We first divide throughout by z power 3, so we get this expression. Next we cross multiply and invert. So on the left hand side you will have yn minus 2 into y of n minus 1 plus y of n minus 2 minus y of n minus 3. So that is what happens when you multiply this and y and invert. Similarly, for the u terms we get the following. It is easy for you to verify this. So yn can be obtained as a weighted sum of past inputs and past outputs. So all that you have to do is to remember the previous u values and previous y values, and you can get an expression for yn directly. So we say that yn can be obtained as a weighted sum of past inputs and past outputs. This recursive realization is available only in discrete time systems. Often complicated state space approach is not required in discrete time systems as a result. So beginners also can easily implement controllers in discrete time. Such a method is not available in continuous time systems. We conclude this presentation with an explanation of a comment I made earlier, that sample systems have at least one delay. Remember, input and output are sampled by the same clock, that is, they are simultaneously sampled. All physical systems have at least some delay, however small it is. It could be a millisecond or a microsecond, but there is a non-zero delay. So by the time input's effect is felt at the output, the clock would have come and gone, because the input and output are synchronized by the same clock. As a result, the effect of an input can be felt at the output not before the next clock pulse. So we say that there is at least one delay in sampled data systems. Of course, there could be more delays. With this, we have come to the end of this presentation. Thanks for joining.